Hi guys, today we're on Unit 10, Lesson 7, and we're discussing more limits and continuity. Just because this is a pretty tricky subject, so I figured we'd devote a second day to it. So far we've been discussing that a continuous function is a function that has no holes, breaks, or gaps. So for instance, if we think about just any random function, a continuous function. Now it can be linear, whatever the case may be, but it's a function that you can basically draw the whole graph without lifting up your pencil. Specifically, when we want to see if a function is continuous at some value c, we want to make sure that the function value and the limit are the same number. So by our definition of continuity, again, that means when we plug in some number, we get an answer. When we evaluate the limit as x approaches that number, we get an answer. And depending on what the function is, we may need to evaluate one-sided limits. Okay, so we have to be careful at that step. And the last thing we do is match them up. If the two numbers match, then our function is continuous. Okay, so whether you are evaluating a limit or determining whether a function is continuous at a specific value, always consider what type of function you're dealing with before you begin your problem. Okay, think about the behavior of that function. Using the definition of continuity, determine whether the graph of h of x, which is equal to x cubed minus 4x over x squared plus 8x minus 20, is continuous at each of the following x values. And we're going to justify. So we are going to work a little bit on why it would or not be. All right, so rational function. Whenever I'm dealing with a rational function, I know that my denominator is going to be affect what happens, right? When the denominator is 0, I either get wholes or asymptotes. So what we're going to do is when we go to evaluate at x equals 2, I'm just going to start by plugging in 2. 2 cubed minus 4 times 2, 2 squared. So 8 minus 8, I'm going to get 0. 4 plus 16 is 20. 20 minus 0 is 0. Undefined. Remember, as soon as something fails, as soon as a condition fails, that means not continuous. You don't even have to continue on, depending on the type of problem. But we wouldn't even have to bother. It's not continuous because f of 2 is undefined. When x equals 0, well, let's see what happens here. Start by plugging in 0. 0 cubed minus 4 times 0. 0 squared. 0 over negative 20. So when I plug in 0, I get 0 as my answer. So I got an answer. I move on to step 2. Now I'm going to evaluate my limit. The limit as x approaches 0 of this function. Well, once again, when I go to evaluate my limit, the limit as x approaches 0 is 0. I don't know why I'm writing it all big again like this, but that's okay. When I plug in a number, I get an answer. When I evaluate the limit, I get an answer. Do these two numbers match? Since they do match, yes, it is continuous. Because f of 0 matches the limit as x approaches 0. Or vice versa, you could write it in either order. When x equals -10. So what am I going to do? Oh, I should have been using h this whole time. I'm sorry. We'll use h for this one. H of -10. What happens when I plug in -10? Oh, I don't even want to do these numbers, but -10 cubed is going to be -1,000 plus 40. So whatever that is, I get some number in the numerator. I might as well be good about this. -1,000 plus 40, -960. And what is this? 100 minus 80 minus 20. That's going to be 0. When I plug in -10, I don't get an answer. So once again, not continuous at x equals -10 because f of -10 is undefined. Now, in some instances, you may have to do more work, but this is just like the basic gist of things, okay? That's how you would approach that type of problem when it's a rational function. Determine whether the function is continuous at x equals 3. Our function here is a piecewise function. Oh. That should say f of x equals. I'm sorry about that. So f of x equals x squared minus 9 over x minus 3 if x is less than 3, 9 if x equals 3, and x squared minus 3 if x is greater than 3. If we want to determine whether the function is continuous, we're going to first plug in 3 and see what happens. When I plug in 3, I get 9 as my answer. Now I'm going to evaluate the limit as x approaches 3. So when I go to find the limit as x approaches 3, I have to remember piecewise functions behave differently. So when I go to evaluate, I have to evaluate in that function. That's my left limit. And that's going to be my right limit. So I have to break this up into two limits. When I evaluate 3 from the left, I'm starting with just plugging in. 0 squared minus 9, 0 squared. 3 squared minus 9 over 3 minus 3. 0 over 0. Since I didn't get an answer the first time around, I have to factor and try again. This time when I plug in 3, I do get an answer, and that answer is 6. That's my left limit. My right limit, when I plug in 3, my answer is 6. If my left limit matches my right limit, that means my overall limit is 6. Now I go back and I compare my function value to the limit. If they're the same number, your function is continuous. Since these are not the same, this function is not continuous at 3 because f of 3 does not equal the limit as x approaches 3 of our given function. Okay. So I just, wanted to go back and review some different situations and just to sort of solidify things for you guys. Now let's see if we really know what we're talking about. And this is like a typical AP style question. For what values of the constant c is the function going to be continuous over all real numbers? So think about what needs to happen. Our function value has to match our limit. So what would I get when I plug in 3? Well, f of 3 equals, I'm using that function to evaluate. If I plug in 3 for x, f of 3 is going to equal 3 times c plus 1. Now I'm going to evaluate my limit. The limit as x approaches 3. When I'm less than 3, I'm using this rule. When I'm greater than 3, I'm using that rule. So this is like a little backward thinking because now we're finding what value of c is going to make this work. So the limit as x approaches 3 from the left, the limit as x approaches 3 from the right. I'm using that rule. I'm using that rule. When I plug in 3, I get 3c plus 1. When I plug in 3, I get c times 3 squared minus 1, or 9c minus 1. This and this are the same already. So in order for my function value to match my limit, I've got to make sure that these two are equal to each other. Oops, I got this squared. Oh no, that's right. So basically, to finish up this problem, I'm just going to set 3c plus 1 equal to 9c minus 1 and solve this equation. Solve for c. So negative 6c equals negative 2. C is going to equal negative 2 over 6. So if c is 1/3, right? If I put 1/3 in front of each, then this function will be continuous at that value. Okay. I'm going to give you guys a few minutes. It's not in your lesson, but I'm going to have you guys practice one on your own. Find the value of a so that f of x is continuous at x equals 2. And here's your function. Okay. So just, you can pause your video, whatever you want to do. Just take a moment and see if you can solve that. Okay. And I'm going to do the work right now, and you can check your answer when you're done. So for this example, if A equals 1, the function will be continuous when x equals 2. And here, all you really had to do, right, was set these two guys equal to each other and solve that equation. Okay, so that's it for this unit. Make sure you work on your review sheet, and we will see you soon.